So what are we going to do when we have to find V, which is electrical potential of a uniform line of charge, okay? So we have to find the V, electrical potential of a uniform line of charge. We are going to start where we always started with, I don't know, a line of charge, right? I don't want to make it into a cylinder, but I'm just going to talk about a line of charge. Okay. We know from when we were calculating electrical fields, we know dq equals lambda dz. If we consider this to be our z-axis, right? If we consider this to be our z-axis, then this will be y, and so x will be coming out, okay? And we have to find the potential at, say, this point P. I'm just coming up with these points randomly, right? This means what I'm going to have to do is to divide these into small volume elements, each of spacing dz, and each of these having dq charge, okay? So we said V will be equals to K sigma dq over R, okay? That is a general formula we are always going to start from. So what is our R? R is going to be this distance here. But I know that R equals y, and z. So R will equal y squared plus z squared square root. Okay? And dq will equal lambda dz, where lambda is the charge density. So this is now going to become K sigma lambda dz over y squared plus z squared, right? And the limits of integration are going to be from L by 2, minus L by 2 to L by 2. So I'm going to put those in here as well. Now, lambda is constant, right? So I can take that lambda out of integration, and I will place it here. Okay. Now it's left for me to integrate this. Ooh, I'm missing a square root, right? So that's my integration. Okay, so what is the integral for this? It is going to be log of z plus square root of y squared plus z squared, from minus L by 2 to L by 2. Okay? Once I have that done, all I have to do is plug the values of L by 2 and minus L by 2 into the places where z is, and I can have log of L by 2 plus square root y squared plus L by 2 squared divided by L by 2 plus square root of y squared plus L by 2 squared. And in order to do this, I have used the property here of log, which says log of A minus log of B equals log of A over B, right? So once I plug in this value, when I plug in this into here, I'm going to call it A, and when I plug this into here, I'm going to call it B. Please make sure you understand how I plugged in these numbers. So again, think about it. That really complicated equation is actually not that complicated anymore. It's pretty simple and straightforward. Okay, now let's talk about some limiting cases, right? What are the limiting cases in this scenario? Okay, number one, what happens when y goes to infinity? Well, as y goes to infinity, your point P moves further and further away, right? That means potential at that point, at infinity, is going to be 0. Number two, what if y is not at infinity, but y is very large? It's still large, so then v cannot go to 0, but what happens? Y will become much greater than L, right, which is the length of it. And that means y squared will become much, much greater than L squared, which means I can rewrite y squared over L over 2 squared to be about equals to y squared, right? That I all know. So once I have these values done, I can plug those into here, and this expression will now reduce down to k lambda log of L plus 2y divided by minus L plus 2y. So this going from here to here requires at least 4 steps that I am missing, which you guys have to plug in. So you have to plug in this value, and you have to plug in those values, solve it to get these.